There are 100 billion stars in our galaxy, the Milky Way. Or maybe there are 200 billion. Or maybe 400 billion. No one really knows. In the universe, there are 100 billion galaxies, and as technology improves, that number could increase to 200 billion galaxies. No one is certain. At the start of the 20th century, there was only one galaxy, our own. Clearly, over the past 100 years, our knowledge of the universe has expanded, but there's still a long way to go. After more than 40 years, Voyager 1 has left the influence of the solar wind and is heading for interstellar space. Most of its instruments have been switched off and its nuclear battery is running low. It will be many thousands of years before it reaches anything other than interstellar debris. By then, the craft will be long dead. Cosmic distances are so vast that sending a probe to investigate anything beyond our solar system is not practical. The only realistic way we have of exploring the universe beyond our neighborhood is by examining the light that reaches us. The telescope is the main tool we have for this investigation, and for centuries astronomers have been building ever larger instruments to see deeper into the cosmos. In the 20th century, conventional telescope design reached its limit. Past 8 meters in diameter, the curved primary mirror becomes so heavy that it will sag. As it is aimed at different targets, its precise curve is distorted by the effects of gravity. In addition, any extra resolution gained by the larger mirror is not delivered because of atmospheric distortion. One way to solve both these problems is to put a telescope in space. The Hubble Space Telescope is the best-known example. While the absence of atmospheric distortion was a breakthrough producing very sharp images, both operational and maintenance costs are considerable, and there are launch constraints on the size of a telescope that can be delivered to orbit. But engineers have developed a new generation of Earth-based telescopes with segmented mirrors that overcome the limits to size and can nullify much of the distortion caused by the atmosphere. The twin Keck telescopes on Mauna Kea in Hawaii were early adopters of this technique. Both have 10-meter mirrors, each in 36 hexagonal segments. Sensors monitor the mirror's shape, and actuators behind each segment continually correct for any distortions to the curve. The system is called active optics. A similar system that works at a more rapid rate monitors the stability of a bright guide star, or an artificial guide star generated by a laser. The adaptive optics system reads wavefront changes in the atmosphere, then adjusts the mirror's shape to minimize any distortion. This image of Jupiter, using adaptive optics, rivals those captured by an orbiting telescope. Observatories are located at high altitude, where the air is dry and there is no light pollution from nearby cities. The European Southern Observatory has clusters of telescopes at several sites high in Chile's Atacama Desert. At Paranal, 4 identical large telescopes each have 8.2-meter mirrors. They can combine their light using interferometry. In addition, 4 auxiliary 1.8-meter telescopes can link into the cluster. Collectively, they are the Very Large Telescope Interferometer, or VLTI. Visible light is just a small part of the electromagnetic spectrum. ESO has another facility northeast of Paranal on the Chaknantor Plateau. Here, an array of 66 radio dishes observe in millimeter and sub-millimeter wavelengths. They are linked and also function as an interferometer. Observing in the microwave part of the spectrum is particularly useful, as these frequencies penetrate gas and dust clouds that remain opaque to higher energy signals. The more widely the telescopes are separated, the better the angular resolution they can deliver. This property led radio astronomers around the globe on a unique collaboration. If radio telescopes around the world could link up, perhaps they could see the unseeable. General relativity predicted bodies so massive, with such strong gravitation, that not even light could escape from them. They were called black holes, and at first they were regarded as a mathematical anomaly. But evidence mounted suggesting that black holes were more than just a theoretical curiosity. At the center of some galaxies, light far more intense than could be expected from stars has been detected. Massive bodies, such as young stars, attract diffuse matter, which begins swirling and flattens into what's called an accretion disk. Just as planets orbit stars, it's now accepted that galaxies orbit supermassive black holes. The very bright light comes from the accretion disk surrounding the black hole. Matter in the accretion disk is accelerated to incredible speeds, generating intense heat. Along the axis of rotation, jets of ionized material are ejected at close to the speed of light. Computer modeling indicated that the vast energy generated by a black hole's interaction with material in the accretion disk could be detected. The silhouette is the event horizon, the boundary beyond which light cannot escape.
If you want to make a test of the fundamental theories of the universe, you want to go to the most extreme laboratories in the universe, and a black hole is that.
Astrophysicists knew that by linking widely separated radio telescopes, the resolving power of the combined instruments would increase dramatically. The first attempt at imaging the black hole at the center of our own galaxy was made in 2006 using instruments in Arizona and Hawaii. It was not successful, but researchers learned a lot, realizing more telescopes were required. By 2009, an international collaboration between 8 different telescopes had coalesced. They aimed to capture an image of the supermassive black hole at the center of Messier 87.
So for this experiment, it was clear that we need expertise from completely different areas. And so we needed someone with imaging capabilities, we needed someone with numerical relativity capabilities, and in my case, we needed someone who can try to find this additional information via pulsars. And so just being part of this team means you work completely differently.
The project was named the Event Horizon Telescope. Instruments in North and South America, Europe, Hawaii, and even in Antarctica would unite to form a telescope with a virtual diameter equal to the Earth. None of these facilities was designed to work as part of such a large array, and the technical difficulties facing the team were immense. Signals from all the sites would have to be processed at a central location, yet the distances that separated them were so great that a direct line linking them was impractical. Data transfer would take place via computer hard drives that were moved from the place of acquisition to 2 locations, the Max Planck Institute in Bonn and the MIT Haystack Observatory in Massachusetts.
The Event Horizon Telescope collaboration is a collaboration of more than 200 scientists with different backgrounds. They all come from different parts of the world. They have different experiences, different set of skills. These are engineers, observers, theoreticians, And they all work together not only to image the event horizon of a black hole, but also to understand what we're seeing.
Theoreticians already understood that while a black hole could only ever appear as a silhouette, its influence upon light emanating from surrounding matter would be dramatic. By using mathematical simulation, NASA came up with a moving image of what they thought the EHT project would reveal. Viewed from above, the swirling accretion disk appears without distortion. The smooth inner circle is the photon ring, light in orbit just outside the event horizon. When viewed from the side, the black hole's gravitation bends light from the accretion disk so it can be seen from several angles at the same time. But no one really knew what they would see. For decades, evidence had accumulated that a black hole at the center of galaxy M87 was consuming huge amounts of material. Unusually high emissions across the electromagnetic spectrum were detected in this region, and images from the Hubble Space Telescope revealed a huge jet of matter extending out light years. In April 2017, the EHT was scheduled to make a series of coordinated observations of the heart of the M87 galaxy. Each observatory had been equipped with its own atomic clock, as all data had to be meticulously time-stamped. Good weather had to happen simultaneously at each site, and a go, no-go decision was made several hours before each observation. April the 5th, 6th and 7th had good conditions, with data being collected. Observations were suspended on the 8th and 9th due to strong winds at the sites in Mexico and Arizona, with the final night's observations made on the 10th and 11th of April.
We have this terrible period of waiting where we don't know if it's all worked. We send all of our data together, and only when it's truly combined do we know if it's worked. And then the even harder part begins of analyzing that data and being very, very careful, doing all the checks and balances to know that we got it right.
During the observation period, 5 petabytes, that's 5,000 terabytes, of data was recorded. The hard drives upon which it was stored weighed half a ton. They were transported to correlators in Westford, Massachusetts, and to Bonn in Germany. While this was relatively simple from most sites, limited access to the South Pole telescope delayed its data for several months. Interpreting radio data as a picture relies upon the black hole's gravitation bending passing electromagnetic waves. The EHT will only be able to see the individual points from rays that are bent toward the Earth. It is the correlation of all these points that builds them into a recognizable image.
Seeing a black hole actually allows us to not only know they exist, and not only know an event horizon exists, it also allows us to test some of the very basic predictions of the theory of general relativity of Albert Einstein, which really describes space and time in its completeness. And that has never been tested before.
In April 2019, the Event Horizon Telescope team released their image of the active center of the M87 galaxy. At its heart was the silhouette of one of the largest black holes we know. It's roughly 38 billion kilometers across, the diameter of our solar system. Its mass is 6.6 billion times greater than our Sun. After predictions flowing from the general theory of relativity more than 100 years ago, the world finally has proof that black holes do exist. But this is not the end for the EHT team. Expanding the number of telescopes in the network will enhance resolution, and there are plans to investigate the black hole at the center of our own galaxy.
The future of this project is amazing. Right? We have done something extraordinary. We've made the first picture of a black hole, but now we want to do even more. Now we want to make the first movie. Now we want to understand how space-time rotates around the black hole. We'll do that by putting more telescopes around the world to make our virtual lens even better.
Investigation into black holes is not restricted to radio astronomy. The New Technology Telescope at La Silla in Chile, the first instrument equipped with active optics, began long-term observation of the stars at the center of our own galaxy in 1992. The NTT observed in the infrared part of the spectrum because only that light was able to penetrate the heavy clouds of gas and dust shrouding the central regions of the Milky Way. A team from the Max Planck Institute plotted the positions of the stars, building up an image of the way they moved. They began using the larger telescopes of the European Southern Observatory at Paranal when they came online. Over 16 years, they mapped the paths of 28 stars.
Well, you see, the Milky Way Center is one of the most important laboratories we have to study in very great detail what's happening in centers of galaxies, in much more detail than we can ever hope to do in all other galaxies. Yet, here we are, we can study whether there's a central black hole, what happens around it, and so forth. All very general issues which we would like to explore and which you cannot really study that much in detail in other galactic nuclei.
Results showed that the stars are orbiting an invisible point, which must be our own galaxy's black hole. Analysis of their highly eccentric paths suggests the Milky Way's black hole is slightly greater than 4 million times the mass of our Sun. Of particular interest is the star S2, which is in a 16-year orbit of the black hole. Its elliptical path was due to take it to its closest pass and its highest speed in April 2018.
We want to use it as a tool to test whether general relativity, the theory of Einstein, is actually wrong or right.
General relativity predicts that the black hole's influence would distort S2's light toward the infrared as it reached 3% of the speed of light, which happened, yet another vindication for Einstein. This test is important to researchers because general relativity predicts that time stops inside a black hole's event horizon, and they want to know if the laws of physics break down approaching these extremes. Since Copernicus proposed that the planets orbited the Sun, astronomers have speculated about planets orbiting other stars. Advances in telescope technology allowed researchers to see dips in the brightness of stars that could only be caused by a transiting planet. These fluctuations in intensity gave astronomers clues about the planet's size and its orbit. A different method monitored the spectral shifts in a star's light caused by a consistent change in its position, again only explicable by an orbiting planet. Using these systems, telescopes around the world began cataloguing exoplanets. But the methods used were biased toward finding large planets, similar in size to Jupiter, that had an easily detectable influence on their star. And of all the planetary systems out there, researchers could only use these methods for planetary systems that were edge-on to the Earth. Even so, the number of exoplanets we knew about continued to grow. There were surprises. In 2012, a French team discovered an orphan planet wandering across our galaxy. It had no star. It was detected by its emissions in the infrared. It's difficult to predict the orphan planet's size, but it's certainly still at the very least several times the mass of Jupiter. Naturally, researchers were keen to see Earth-sized planets, planets that could possibly nurture life. When a new and highly accurate spectrometer called HARPS was installed at ESO's La Silla 3.5-meter telescope, this became possible. Among its discoveries are two planets orbiting Gliese 667c, about 20 light-years from Earth. The star is a red dwarf, about 1/3 the mass of our Sun. Of particular interest is Gliese 667c-c. a planet about 5 times the mass of the Earth, and at a distance from its star that puts it in the habitable zone. Statements about conditions on Gliese 667cc have such a large margin of error that much more work needs to be done before it could be declared a possible venue for life as we know it. Another star, 40 light-years away, has a greater range of possibilities. TRAPPIST-1 is an ultra-cool red dwarf star orbited by 7 planets, all of them close to Earth in size. To date, this is the largest number of exoplanets detected orbiting an individual star. At least 3 of the planets are considered in the habitable zone. Many different observatories have been gathering data about the TRAPPIST-1 system, but we still know so little about what kind of environments the different planets might have. However, the coming generation of telescopes should be able to analyze the atmospheres of the TRAPPIST's planets, so they will remain a region of close study into the future. At the moment, around 3,800 exoplanets have been catalogued, and that number continues to grow. In 2018, the satellite TESS was launched to search for more exoplanets. To have a clear view of both the northern and southern skies, TESS was placed in a 14-day orbit around the Earth at a 40-degree angle to the plane of the Moon's orbit. It will systematically map 26 segments of the sky, recording fluctuations in the brightness of nearby stars that reveal exoplanets. During its close passes of the Earth, the Planet Hunter downlinks its data to sites across the United States. Ground-based observatories will then follow up leads in a more detailed way. This type of collaboration between orbiting and terrestrial telescopes is becoming common. An interesting discovery came from the young star Beta Pictoris. Fluctuations in its light did not bear the rhythmic signature of an orbiting planet. Further investigation by the European Southern Observatory revealed 3 comets orbiting the young star. Beta Pictoris is only around 20 million years old and still displays a protoplanetary ring of dust. In TESS's first year of operations, at least 29 new exoplanets were confirmed, with a further 1,000 objects of interest listed in publicly accessible databases. During its 2-year life, TESS will image 200,000 celestial bodies, including 1,000 of the closest red dwarf stars. And there will soon be a new Planet Hunter in orbit. The Wide Field Infrared Survey Telescope, WFIRST, will use a different technique known as gravitational microlensing to detect much smaller exoplanets. As one star passes in front of another, its gravitation distorts the distant star's light. By monitoring the light over time, a spike in what should be a regular curve reveals an exoplanet orbiting the lensing star. But that's not WFIRST's only objective. There's a gap in knowledge that some cosmologists find embarrassing. When quantifying the speed at which galaxies rotate and the amount of mass they contain, there's a baffling mismatch. Our laws of physics say that spinning galaxies do not contain enough matter, and therefore enough gravitation, to prevent them from flying apart. And yet, they don't. Astrophysicists came up with the dark matter hypothesis. This is not just matter that doesn't glow. It is matter that interacts with nothing else. The only influence it has is via gravitation. Halos of dark matter surrounding galaxies is the current method to explain why they move the way they do. Estimates say there is 5 times more dark matter than matter, yet no one can explain it. Another fascinating anomaly is that early galaxies, galaxies whose light has taken more than 10 billion years to reach us, rotate at a slower rate. The influence of dark matter is not as pronounced. New generations of telescope are being built to help researchers answer some fundamental questions about the laws governing the universe. But it seems that cosmology has reached a stage where it is just discovering how little we know about what lies beyond the solar system. The space industry is at a turning point. NASA's Space Launch System is about to fly. With it, the new Orion spacecraft, a collaboration between NASA and ESA, will target the Moon. A landing is scheduled for 2024. As far as the United States is concerned, low Earth orbit is now the province of corporations, with Boeing and SpaceX competing to break Russia's stranglehold on manned trips to the International Space Station. New technology is cutting costs and increasing launch frequency, with complex satellites being so small they can be deployed in new ways. Several companies are working towards space tourism. Virgin Galactic says its promised trips beyond the atmosphere should start happening soon. Since the retirement of the shuttle in 2011, space science has shifted focus to research carried out on the International Space Station and to robotic missions in deep space. During this period, all manned flights have been to and from the ISS, with the only viable spacecraft being the Russian Soyuz. This has cost both NASA and ESA billions in launch fees. Russia, Europe and Japan, major partners in the ISS, developed their own cargo craft to resupply the space station. But NASA tendered for private companies to take on these responsibilities. Rising star in the launch business, SpaceX, was contracted to develop a cargo craft that would launch on its Falcon 9 rocket.
3, 2, 1, 0. And launch of the SpaceX Falcon 9 rocket as NASA turns to the private sector to resupply the International Space Station.
A second aerospace business, Orbital Sciences Corporation, now Orbital ATK, signed a contract for similar hardware and services. NASA is developing its own launch system and the Orion spacecraft, but it's designed for missions far more ambitious than resupplying the ISS. America's activity in low Earth orbit is being reallocated to the commercial sector, and NASA is helping with technology transfers. Agency administrators want two completely different systems, giving the space agency what they call dissimilar redundancy. When the Space Shuttle twice suffered catastrophic failures, NASA was stuck on the ground for years while exhaustive investigations were made. The redundancy approach will prevent this paralysis. In 2014, NASA signed contracts with Boeing and SpaceX to develop and test human-rated spacecraft to ferry astronauts to and from the International Space Station. It was a continuation of the dissimilar redundancy approach. The space agency has set performance criteria for the new craft and crew training, but is taking a hands-off approach regarding how the companies meet the requirements. Boeing's spacecraft is called the Starliner. It has space for 7 astronauts and will be capable of being used 10 times. NASA requires any human-rated spacecraft to meet higher standards of safety and reliability than a cargo craft. And new capsules must demonstrate, via a series of test flights, that they meet certification. One crucial part of the new spacecraft is the launch escape system. It's the equivalent of a fighter pilot's ejector seat. Both Boeing and SpaceX have opted for a new method of capsule-mounted rockets to push the craft clear in an emergency, in contrast to the more traditional escape tower above the agency's new Orion spacecraft. The trial of Boeing's escape system worked well, with the exception that only 2 of the 3 parachutes deployed, but the problem is understood. The Starliner could continue to the next uncrewed launch to orbit. One of the novel features of Boeing's capsule is its ability to return to dry land, like Russia's Soyuz craft. Airbags, stowed behind the heat shield, inflate prior to landing. Without the need to deploy ships for an ocean recovery, there will be considerable savings. Though the capsule can fly on the Delta IV, the Falcon 9, and the yet-to-be-flown Vulcan, initial testing of the spacecraft has been with the Atlas V launcher. The Atlas ground support infrastructure has been modified to accommodate the Starliner with the addition of a crew access arm. The Starliner made its first unmanned test flight in December 2019. Its destination was the ISS. The launch was perfect, and 4.5 minutes after liftoff, the first stage separated. Next, the boost protect covers and the aeroskirt were jettisoned, and the Centaur upper stage burned for a further 7 minutes, following the course parameters perfectly. After separation, the capsule was in a suborbital trajectory, selected because it allowed a safe path back to the ground in case of a malfunction during the boost phase. To achieve the correct orbit, the craft was required to fire its 4 attitude and orbital maneuvering thrusters 31 minutes after liftoff. However, the Starliner's sequence clock was incorrect, and the orbit insertion burn did not happen. Ground control was able to salvage parts of the mission, but the craft was not able to reach the International Space Station. This setback will delay the Starliner's first mission carrying astronauts. SpaceX's Crew Dragon capsule is a refinement of the cargo craft that first flew in 2010. From the beginning, the Dragon capsule has had a heat shield, enabling it to return safely to the ground. No other ISS cargo craft has had this ability. In addition, the Dragon also has a window. This should have been a clue to SpaceX's long-term plans for the craft. In 2014, after the contract for a human-rated craft was signed, SpaceX began work on the Dragon 2. Like its Boeing equivalent, the Dragon 2 sits above a service module that can carry unpressurized cargo and includes a heat exchange unit and a coating of solar cells that does away with the moving parts involved in extendable solar wings. The Dragon 2 can accommodate 7 astronauts, though NASA has said it will generally only send 4 people at a time. Control interface is via a touchscreen. Cape Canaveral's Launch Complex 39A has been equipped with a crew access arm, and in March 2019, in a flight known as Demo 1, the unmanned craft made its first spaceflight. The Dragon carried a dummy astronaut, wired with sensors to monitor G-forces, and a small delivery of equipment for the ISS. The launch and the phasing maneuvers to align its orbit with the ISS were all correctly executed. The automated docking procedure went smoothly, and the Dragon stayed connected to the space station for 5 days. Decoupling from the ISS went as expected, and observers on the ground were delighted with the capsule's behavior. Throughout the mission, every aspect of the Dragon 2's performance was monitored. The craft's return to Earth was faultless, and the recovered capsule would be reused for the one remaining uncrewed flight test. SpaceX planned to use new capsules for manned flights and then recycle the craft for cargo use. Confident planners at SpaceX and NASA were looking toward the first crewed flight. The final certification test was an in-flight simulation of a booster failure that would monitor the Dragon's launch escape system. But before that, the craft's Super Draco engines, used in mission aborts, needed retesting. This was considered routine and had been carried out many times. A leaked video revealed an explosion that had destroyed the capsule. The problem was not engine failure, but a faulty valve. The flight test of the Dragon 2's escape system eventually happened early in 2020. But just as with the Boeing capsule, which was also well behind schedule, the explosion and the inquiry that followed were another unwelcome delay.
2, 1, 0. Ignition.
Of maximum dynamic pressure, the core stage's engines were cut and the escape system triggered automatically. Shortly after, aerodynamic stresses on the tumbling booster caused it to explode.
Cheering in the room, bright flash there. It looks like maybe Falcon 9 breaking up.
The certification test was a success, and the Dragon 2's next flight will carry astronauts. But there is another spacecraft in development that's worth mentioning, the Sierra Nevada Corporation's Dream Chaser. It's a lifting body craft designed to ride to orbit on an Atlas V, but return to the ground via a commercial landing strip. So far, the Dream Chaser's only flights have been glide tests. As a cargo ship, the Dream Chaser can return a 1,750 kilogram load to the surface. As a crewed vehicle, it is designed to take from 2 to 7 astronauts. The European Space Agency has shown interest in the craft, with the possibility of launching European astronauts atop of French Ariane. The craft will use the bipropellants methane and hydrogen tetroxide for on-orbit maneuvers, doing away with the highly toxic hydrazine. When the space shuttle landed, it had to be at a restricted runway where suited ground staff purged the craft of residual hydrazine. Originally in the running for a NASA contract for ferrying astronauts to the ISS, it missed out because Sierra Nevada could not comply with NASA's 2017 deadline for crewed missions. The favored contractors, Boeing and SpaceX, both failed to meet that same deadline. But the Dream Chaser has a contract for cargo missions to the ISS, and an expendable cargo module known as Shooting Star is being developed. The company still plans a human-rated version of the Dream Chaser, but it's unclear when the craft will fly.
Burn! 4, 3, 2, 1. Burn the hole! Burn the hole!
Cape Canaveral's Launch Complex 17 was the starting point for many historic Delta II missions. Since the demise of the space shuttle, NASA infrastructure from the earliest days of spaceflight has been eliminated. Since the heady days of the space race, NASA's budget has been steadily trending downward, and various launch sites have been given over to the private sector. While NASA has been overseeing the commercial craft that will continue to service the research work carried out on the ISS, its sharpest focus has been on the new Orion spacecraft and the giant Space Launch System that will boost it to orbit. After its establishment in 1958, the agency's challenge had been to master space technology and then to reach the moon. But since then, the exploration side of NASA's charter has been achieved by robotic missions. Now, a new plan called Artemis will return to the moon. It relies upon the Orion spacecraft and the SLS. The Space Launch System will be the most powerful rocket yet built. And although the design features the latest technologies, most of its components are derived from the Space Shuttle. The Block 1 version, which will send an unmanned Orion spacecraft to orbit the moon, features a central core that owes much to the shuttle's external tank. At the base of the central core are 4 RS-25 engines. The shuttle had 3 of these engines, and NASA still has 16 left over from the shuttle program. Although the engines remain the same, their control systems have been redesigned. Each one has been exhaustively tested, and when the original batch have been utilized, an upgraded version, the RS-25D, will be available. Flanking the central core of the Space Launch System are 2 solid fuel boosters. Again, a refinement of shuttle technology, but with each booster having 5 instead of 4 segments. The new design has been rigorously tested. The boosters will only burn for the first 2 minutes of flight, each consuming 6 tons of propellant every second and providing more than 75% of the rocket's thrust. Unlike the shuttle's boosters, these will not be reusable. The upper stage for the Block 1 configuration of the Space Launch System is called the Interim Cryogenic Propulsion Stage, the ICPS. It's a stopgap modification of the Delta Cryogenic second stage, used with the Delta 3 and 4 launchers. In 2014, a Delta 4 fitted with this upper stage lifted an Orion spacecraft to its first orbital test. The Orion, with a dummy service module, was boosted to a height approaching 5,800 kilometers, allowing it a high-speed return to Earth similar to a lunar mission. The much larger exploration upper stage was to replace the ICPS for the first crewed mission atop a Block 1B launcher, but design changes have led to delays, and the EUS now won't fly till the 4th Orion mission. The Orion spacecraft itself will comfortably accommodate 4 astronauts for 21 days, with the crew breathing air at atmospheric pressure. The craft is intended for missions beyond Earth orbit. It's designed to integrate with larger modular structures such as habitation modules, specialist landing craft, or the planned lunar gateway. Instrumentation and the control interface are primarily via a touchscreen. The digital control enables weight saving through the absence of wires and switches. The Orion Service Module is the European Space Agency's contribution to the craft. It's derived from the automated transfer vehicle which delivered cargo to the ISS. Oxygen and nitrogen cylinders in the service module supply air. There's a water storage tank, and wastewater is not dumped but recycled. A 4-wing solar array generates 11 kilowatts for battery charging and powering the electrical subsystems. For propulsion and maneuvering, the service module is equipped with a version of the same system used by the Space Shuttle. But like so many aspects of this spacecraft, the system can be easily replaced when alternate models under consideration become available. The third important piece of the Orion craft is the launch abort system, mounted above the capsule. 3 different types of solid fuel rocket are designed to fire at the first hint of a malfunction in the launcher.
1. Ignition.
The system was tested in July 2019 above a Minotaur booster, a highly modified peacekeeper missile. Engineers were delighted with its performance. Launch infrastructure is being upgraded for the SLS, and there's increased activity in preparation for the first test of the big new rocket. There were celebrations as the core stage left the Michoud assembly facility. But it hasn't gone to Cape Canaveral, not yet. It was taken by barge to the Stennis test facility in Mississippi, where the stage will be powered up for a series of tests known as the Green Run test campaign. The date, or even the year, for the first launch has been put back a number of times, although it could be as early as 2020. NASA's Exploration Initiative received a jolt in 2019 when US Vice President Pence, the chairman of the National Space Council, called for NASA's Exploration Initiative to be accelerated.
It is the stated policy of this administration and the United States of America to return American astronauts to the moon within the next 5 years. And now's come the time for us to make the next giant leap and return American astronauts to the moon, establish a permanent base there, and develop the technologies to take American astronauts to Mars and beyond.
The existing plan had called for a moon landing no earlier than 2028. The month after the Vice President's speech, NASA announced the Artemis program, Artemis being the sister of Apollo. Late in 2019, companies were called to tender for a lunar lander and for a lunar space station known as the Lunar Gateway. The timeline calls for Artemis 1, an uncrewed Orion craft, to enter a series of looping orbits of the Moon in 2020. Astronauts are in training for Artemis 2, due to launch in 2022. The current proposal will see a crew of 4 sent to a retrograde orbit of the Moon in a flight that could last as long as 21 days. The powerful exploration upper stage will not be ready for this flight, and its proposed trajectory has been modified to accommodate the limited capacity of the interim cryogenic upper stage. During this time, the Artemis plan calls for commercial launch services to make a series of uncrewed flights to position elements of the Lunar Gateway and Lunar Lander in orbit around the Moon. A contract has been signed with Maxar Technologies for a power and propulsion element. Some see this phase of the Artemis program as a weak link, because the US Congress has been reluctant to authorize additional funds. There are no concrete blueprints for a lunar lander yet, and some have suggested that the 2024 deadline is being pushed too enthusiastically. Artemis 3 will see a male and a female astronaut land near the lunar South Pole, where ice exists within permanently shaded craters. Long-term goals for NASA's Space Exploration Initiative include the development of technologies that will enable a landing on the surface of Mars. Finally, a different form of spacecraft will soon be taking passengers. Virgin Galactic will start taking paying customers to space in 2020. Everything about the company's spaceships, Enterprise and Unity is reusable, and Virgin is building 2 additional spacecraft. Passengers will experience weightlessness for about 6 minutes. Virgin is also entering the satellite business with a launcher service using a 747 called Cosmic Girl, acting as an air launch mothership. The Earth is our home. Our natural environment results from complex relations between the sun, the oceans, and the atmosphere. The polar ice and the tropical heat represent the extremes of our planet's climate. In reality, this is a very narrow temperature band, completely different from any other planet we've observed. The stability of the Earth's environment has allowed life to emerge, and life has changed the planet. As far as we know, the Earth is the only planet in the universe to have given rise to life. The Orion Nebula is a vast cloud of gas and dust in the Orion constellation. It's a place where new stars are being created. As part of the nebula condenses, it separates into clumps. As each clump contracts under its own gravitation, it begins to swirl, flattening into a disk. They're called protoplanetary disks, or proplyds. In the center of a proplyd, as the molecules are squeezed together, a fusion reaction begins and a star ignites. Some proplyds, occurring close to an established star, shine brightly under the influence of their neighbor. While this makes them easier to observe, the glowing gas and dust is being stripped away by the stellar winds from the adjacent star. Dark proplyds, only observable as silhouettes, maintain their surrounding ring of gas and dust. As the system matures, this stellar debris will form a planetary system. The Hubble Space Telescope has recorded numerous examples of this process, enough for astronomers to understand that the formation of planets is commonplace. This is how our own sun started its life 4.6 billion years ago. But the planets would take longer to emerge. Small grains within the disk began accreting, forming planetesimals. The larger a clump became, the stronger its gravitational attraction, in turn leading to more rapid growth. An early version of Jupiter would have been the first to coalesce, completely clearing its orbit. Around a core of heavy metal and rock, Jupiter's atmosphere, mainly of hydrogen, was compressed by its strong gravitation. Any solid surface lay beneath thousands of kilometers of liquid gas. Our observations of exoplanets have revealed Jupiter-sized gas giants orbiting close to their stars. Astronomers believe the young Jupiter would have begun a track toward the Sun, dragging asteroids and comets in with it. But Jupiter's inward path reversed as it was pushed into an orbital resonance with the emerging Saturn. Not all of the objects forming in the early solar system stayed orbiting the Sun. Smaller objects passing a planet would be deflected by the stronger gravitation, or even captured, becoming a moon. It is thought that there were up to 20 smaller planets orbiting in the inner solar system, from which the 4 remaining terrestrial planets were formed. At this time, collisions in the developing planetary system were common, and evidence from the Apollo moon rocks suggest an impact between the early Earth and an ancestor of our moon was important in our planet's evolution. The Earth has a larger than expected iron core, and gravitational analysis of the moon suggests its core is lighter than expected. A collision between the bodies would explain the moon's loss of much of its heavy material to the more massive Earth. The impact was a glancing blow that set the Earth rapidly spinning with a 5-hour day. The moon that we know coalesced from the molten debris. Although our moon is not the largest in the solar system, it is closer in mass to its parent planet than any other moon. The stabilizing effect that the moon has upon the Earth's rotation is significant. Over long periods, the Earth's axis will vary by as much as 1 degree. Without the moon's influence, this variation could be as much as 85 degrees, with drastic implications for the climate's stability. The debris in the early solar system was cleared by the planets in a period called the Heavy Bombardment. The emerging Earth was peppered with asteroids and comets, delivering water necessary for life. While tectonic forces erased the bombardment scars from Earth, the Moon, which endured the same travails, is still covered with craters. When chaos in the developing solar system settled down, the young Earth was in a unique position. The Earth's distance from the Sun was just right for the abundance of water on the planet to exist in liquid form. As the Moon had drifted away, the planet's rapid rotation had slowed, and the Sun's heat was evenly shared across the surface. The Earth's large metallic core, combined with the planet's rotation, meant that a magnetic field stretched out around the planet, deflecting the charged solar wind and protecting the surface from extremes of solar radiation. In a hostile universe, the Earth was a uniquely benign environment. The geological record shows that around 2.7 billion years ago, oxygen began occurring in the atmosphere. The vast iron ore regions of Western Australia were formed as iron in the oceans reacted with the new abundance of oxygen to form iron oxide. Simple plant life was using the sunlight and carbon dioxide to live, and it produced highly reactive oxygen as a waste product. This enabled more complex life to emerge, building an intricate web of interrelated plants and animals, completely transforming the planet. The change in the atmosphere had other dramatic consequences. Oxygen stripped much of the highly insulating gases from the air, drastically cooling the Earth. A sequence of ice ages began. Though there is an abundance of evidence showing planetary glaciation punctuated by warm periods, the factors triggering these cycles are complex. Fault lines are clues to the movement of continents, leading to diversions of ocean currents. The effect of volcanic activity on the atmosphere. And changes in the direction of the Earth's axis with regard to our planet's elliptical orbit around the Sun, all contributors to long-term fluctuations in the Earth's climate. Analysis of ice cores deposited in the Antarctic or Greenland is an accurate way to see how the composition of the atmosphere has changed over the previous 800,000 years. bubbles of air caught between snowflakes before being rigidly trapped as the snow becomes ice can be accurately sampled. One thing is clear. Carbon dioxide reaches a peak of around 270 parts per million during the warm periods and drops to approximately 170 parts per million when glaciation is at its greatest. But from this data, it's hard to know if extra CO2 causes the warming or the warming leads to extra CO2. In 1958, Dave Keeling, working for the Scripps Institute, began recording accurate levels of atmospheric CO2 at the Mauna Loa Observatory in Hawaii. It was the beginning of a unique record known as the Keeling curves. Keeling's graph revealed a seasonal variation corresponding to spring and summer in the northern hemisphere, where landmass and plant cover is greater. During the northern spring and into the summer, CO2 levels dropped because of the increase in photosynthesis. By the 1970s, a disturbing trend had emerged. CO2 levels were in a steady rise. At first, there was uncertainty about the implications. Extra CO2 could trap more heat, leading to a warming effect, known as the greenhouse effect. But some scientists were worried that aerosol pollution could attenuate levels of sunlight reaching the planet, resulting in a cooling environment. As the decades passed, different pieces of evidence were collected. Drill cores from the ocean floor revealed that ice ages had been triggered by Milankovitch cycles, the variations between Earth's tilt and its elliptical orbit. Though these effects were minor, the correlation was obvious. If such a small nudge could alter the climate, perhaps changes in CO2 could as well. Scientists were realizing just how poorly they understood planet Earth.
A Thor Delta rocket blasts aloft from Cape Canaveral, carrying a robot weatherman into orbit for America's...
At the beginning of the space age, scientists were keen to make weather observations from orbit. Launched in 1960, Tyros-1 was the first weather satellite. It was equipped with 2 TV cameras, regularly transmitting images of global cloud patterns. It provided meteorologists with a unique view, and it was followed by improved versions. Because these early satellites were in highly inclined low Earth orbits, the data gathered covered the whole planet, and it was shared across the world. Since 1873, nations had been cooperating on weather prediction via the International Meteorological Organization, which in 1951 became the World Meteorological Organization, an arm of the United Nations headquartered in Geneva. With a UN resolution calling for international cooperation in the peaceful uses of outer space, weather satellites of different nations were soon being coordinated for the benefit of all mankind. In 1964, the Nimbus program began. The series of 7 satellites included a more sophisticated set of sensors. Nimbus was a testbed for new technologies, and it gathered data about different areas. Along with cloud patterns was information about the atmosphere and sea ice. This was the pre-digital age, and all electronic image data was burnt to and stored on 70mm film. Little thought was given to establishing an archive for future reference. The Nimbus program was an early example of Earth observation rather than just a group of weather satellites. And meteorologists started seeing the planet as a complex and interconnected system. Today, a fleet of satellites is in operation, monitoring the atmosphere, the oceans, the ice, the land, and the biosphere. It is now understood that ice, particularly sea ice, plays an important role in the Earth's climate system. polar ice slowly flows to the coasts where it melts, providing a source of cold water that drives the ocean currents responsible for the transfer of heat from the equatorial regions to the poles. These currents also move nutrition, which is important for the survival of life. Global winds also circulate water via clouds, keeping the land moist and able to support vegetation. Plant life in both the oceans and the atmosphere removes CO2 from the air and replenishes the atmospheric oxygen. Both the ice, known as the cryosphere, and the clouds reflect a proportion of the sun's energy back out into space. The extent of the ice and cloud cover are important factors in the Earth's energy budget. As ice melts, it exposes ocean or rock, which absorbs more solar energy. Similarly, cloud cover, or the absence of it, will have an effect upon the land or sea beneath. Vegetation is also an important climate factor, as land plants pump huge amounts of water vapor into the atmosphere. But things are changing. Humanity, simply through weight of numbers, is influencing key elements of the planet's climate system. In 50 years, the Earth's human population has risen from just over 3.5 billion to 7.7 billion today. More people need more resources. And while there have been revolutions in agriculture and in technology, the Earth's reserves are not limitless. In 1979, Europe began launching spacecraft. And while the new Earth observation satellites were revealing changes, scientists were reluctant to reach conclusions about long-term trends. They understood that there was a certain amount of variability in the planet's climate cycle. And though climate science knew about the steady rise in atmospheric CO2 revealed by the Keeling curve, researchers were looking for additional, solid evidence that change caused by human activity was happening. Since 1913, spectroscopy had revealed that a layer of ozone in the stratosphere blocked harmful UV sunlight from reaching the ground. In 1974, Mario Molina, a postdoctoral fellow working on hot atom chemistry, published a paper suggesting that the family of industrial chemicals known as chlorofluorocarbons, or CFCs, could damage the ozone layer. In the 1980s, meteorologists working in Antarctica found the evidence. The polar vortex above the southern continent concentrates the CFCs in the stratosphere. Mother-of-pearl clouds in the polar skies contain ice crystals which, in combination with ultraviolet, split chlorine from the CFC molecule. Each chlorine atom can break down over 100,000 ozone molecules. A large area centered over Antarctica showed almost no ozone. It became known as the hole in the ozone layer. The United Nations began talks aimed at limiting the production of CFCs, and in 1989, an international treaty, known as the Montreal Protocol, capped the production of CFCs and ultimately resulted in a 10-year phase-out of CFC production. All countries signed the agreement, and the Montreal Protocol is seen as a model of international cooperation. In the 1980s, an upward trend in global temperature averages was becoming clear, and a scientific consensus emerged that the burning of fossil fuels was altering the balance of gases in the atmosphere. Most of our planet's fresh water is locked in the polar ice caps. 61% of this ice covers the Antarctic continent. In the north, Greenland is also covered by an ice sheet. There is no landmass at the North Pole, but a large area of sea ice grows and shrinks with the seasons. Seasonal sea ice also fringes Greenland and Antarctica. Ice shelves are a third manifestation of polar ice. These are thick layers of ice that extend into the ocean from the mouths of glaciers. periodically icebergs will break away from these regions. These areas are important to the circulation of global winds and ocean currents. And since 2002, NASA has tracked the prevalence of water in general and ice in particular via the GRACE satellites, which were recently replaced by a similar pair of GRACE follow-on satellites. The two follow the same orbit, and minute changes in the Earth's gravitational field will cause them to change speed, with a variation in the distance between them. This data is accurately measured, allowing researchers to record changes due to variations in groundwater or in ice thickness. During the life of the first GRACE mission, Greenland lost 285 gigatons of ice per year. On average, Antarctica lost 137 gigatons per year. From 2005 to 2016, sea levels rose by 3.7 centimeters due to melting ice sheets and to expansion of seawater. Sea levels have been monitored from space since 1992, initially with the TOPEX Poseidon satellite, and more recently with the JASON series of satellites. JASON 3 uses a precision radar altimeter to measure regional and global variation in sea levels. In the 20 years to 2014, the average rise was 6 centimeters, but the increase is not uniform. The red areas show the greatest rise, with white representing no change, and blue signifying a decrease. The unevenness of the sea surface is due to a complex interaction between ocean currents, the Earth's spin, and the topography of the ocean floor. All these factors must be accounted for to arrive at a baseline against which to measure changes. These blue areas in the Atlantic show a shift in the Gulf Stream. The Camargue region of southern France is a low-lying area at the delta of the Rhône River. In the 1980s, a seawall was built to prevent the encroaching Mediterranean. Over the last 30 years, the coastline here has been pushed back by several hundred meters. Scientists are convinced that a warming global climate is responsible, and that our reliance on the burning of fossil fuels has led to an excess of carbon dioxide in the atmosphere, which traps heat. 93% of this heat has been taken up by the oceans. Data from the Argo network of ocean buoys shows an average warming of 0.9 of a degree Celsius since the 1950s. While this may not sound like much, meteorologists understand how sea surface temperatures drive hurricanes and cyclones, and early predictions of storms of greater magnitude are being realized. Long-standing weather records are being broken and broken again. In 2017, NASA, NOAA and the UK Met Office all agreed that 2016 had been the hottest year on record. Globally, 16 of the 17 hottest years have all occurred since the year 2000. Both NASA and ESA have been monitoring the distribution and concentrations of CO2 in the atmosphere since 1992. This visualization from data collected in 2006 shows the yearly fluctuations of carbon dioxide and carbon monoxide. While most CO2 emanates from the populous northern hemisphere, seasonal fires in Africa, Australia, and South America generate much of the carbon monoxide. Prolonged droughts and more severe forest fires are another aspect accompanying increased levels of atmospheric CO2 that are currently unfolding. Such events inject a huge pulse of greenhouse gases into the atmosphere, magnifying the problem. The European Space Agency's Copernicus program, with its Sentinel Earth observation satellites, has committed to making information about the changing climate freely available to policymakers, businesses, and research institutions. Josef Aschbacher is ESA's Director of Earth Observation Programs.
What you see here on this graph is the CO2 concentrations of the atmosphere over the last 800,000 years. And you see that these values are going up and down in different phases. You see on the blue lines here are indicating ice ages, and the orange lines here are indicating periods between ice ages or periods where it's much warmer. But you also see that over the last 800,000 years, the value was always below 300 parts per million, and suddenly, since the last century, it goes up very steep towards 400 parts per million or even beyond.
Distinguished delegates,
the recent climate summit, COP25, held in Madrid, made little progress toward an international agreement to cut greenhouse gas emissions. While some businesses and economies will have to adjust, that task only gets more difficult as time passes, and far greater adjustments will be forced upon everyone. The Earth is the only place we know that harbors life, but the stability that has enabled this web of life is fragile. Plants and animals interact for mutual benefit. Our benign environment results from the complex and varied creatures with which we share the planet. It's important that we look after our home. From the moment a rocket lifts off, it is tracked and monitored. All vital performance characteristics are relayed back to the ground via telemetry. At huge distances, a probe must be able to communicate. On Earth, to pick up these signals, we use parabolic dishes. They range in size from small domestic units for television reception to the giants of the deep space network. Without these, almost any space flight would be pointless. The very first artificial satellite, Sputnik, was designed with 4 whip antennas and 2 radio transmitters. Soviet engineers saw its main function as announcing to the world that it was there. It transmitted a continuing series of beeps. Ham radio operators around the world could detect the signal. Very few realized that the beeps varied in duration according to the temperature and pressure within the sphere. The signals could also be analyzed for clues to the ionosphere's electron density.
Roger, the clock is operating. We're underway.
Soon, cosmonauts and astronauts were orbiting the planet. When John Glenn made the Mercury program's first orbital flight, 18 different tracking and communications posts were set up along his spacecraft's ground track. As well as local staff, NASA provided each ground station with its own capsule communicator, a flight engineer, and a flight surgeon. Special tracking ships were deployed to maintain communications and monitor telemetry while the spacecraft was crossing the ocean. But even so, the network had blind spots where the spacecraft was out of reach. For the Soviets, communication was even more difficult. During their early space flights, there were no tracking ships, and their terrestrial stations were all in the Soviet Union. when the Soviet Union launched Lunik 1 in 1959, it was intended to hit the moon. It missed and became the first craft to achieve solar orbit. Because it required special tracking infrastructure and was not monitored outside Russia, many in the United States refused to believe that the spacecraft had even been launched. At the time, the world's largest radio telescope was the Mark I installation at Jodrell Bank in the UK. Soon the Russians began sending detailed information about finding their probes to Jodrell Bank as a means of independently verifying their missions. In the early days of the space race, the Soviet Union had big plans for deep space missions. In 1959, construction work began on the Pluton facility in the Crimea. Though the Soviets did not enjoy the financial resources of the United States, they were not lacking in enterprise. The Pluton receiver consisted of 8 dish antennas welded onto pieces from the hulls of 2 war surplus submarines. They were mounted on a steerable frame made from the truss work of a railway bridge. To point the dishes with accuracy, the designer, Evgeny Gubenko, employed the mechanism from the gun turret of a scrapped battleship. The system worked well and remained in service till 1978. It had become clear to the space powers that communications support for low Earth orbiting satellites was very different to that needed for probes traveling into deep space. Deep space missions require much larger, more sensitive dishes with powerful transmission capabilities. Yet these probes' position in the sky changes more due to the Earth's rotation than it does because of the craft's speed. So while the dish has to point with great accuracy, it does not have to move very rapidly. Satellites in low Earth orbit pass close, so a smaller dish is adequate, but it must move rapidly to maintain a precise focus on its target craft. In the United States, corporations were taking an interest in a huge new type of satellite. Researchers were interested in using an orbiting balloon to relay radio signals across continents. Project Echo launched its first inflatable satellite in 1960.
This is President Eisenhower speaking.
A telephone call from President Eisenhower was relayed from Washington to California by bouncing signals off the balloon, which acted as nothing more than a reflector. In 1962, US phone company AT&T built Telstar. It was the first electronic relay satellite. Launched by NASA in July 1962, Telstar was the first commercially funded satellite. Europeans tuning in to see President Kennedy got baseball and then the presidential press conference.
I understand that part of today's press conference is being relayed by the Telstar communications satellite.
Then French singer Yves Montand sang a song to the US. As far as it went, it was a success. But Telstar's low orbit meant it was only available for 20 minutes every 2.5 hours, and Telstar's life was cut short as a result of the Cold War. Both the Soviet Union and the United States had been detonating thermonuclear weapons above the atmosphere to determine whether this was a viable anti-missile strategy. From tests in the Pacific, they discovered that an immense pulse of gamma radiation triggered positive ions and recoil electrons that took out electrical systems in Hawaii and New Zealand, destroyed at least 3 satellites, and damaged several others, among them Telstar. In October 1963, US President John Kennedy added his signature to a treaty with the Soviet Union banning nuclear testing in space. The first telecommunications satellite that resembled today's technology was Intelsat-1, also known as Early Bird. It orbited above the equator at the same rate as the Earth's spin, which allowed it to hold a static position. It could relay 1 TV channel or 240 telephone calls. It was the beginning of the space business's most profitable industry. Estimates put satellite telecommunications revenues for 2019 at $2.4 trillion US. Geosynchronous orbits make ground stations much simpler without the need to track a target across the sky. Today, there are at least 240 active satellites in equatorial orbit at geosynchronous altitudes. Not all are communications platforms. Weather satellites also find this orbit useful, having an uninterrupted view of a complete hemisphere. The craft must be carefully spaced to avoid collisions and radio frequency interference. The International Telecommunications Union coordinates the orbital slots and frequency allocations, and satellites nearing the end of their useful life must retain enough fuel to boost themselves into a graveyard orbit to prevent overcrowding. There is clutter caused by spent upper stages and old satellites. Another highly specialized group of communication satellites is also stationed in geosynchronous orbit. NASA currently operates 10 tracking and data relay satellites, TDRS. Originally designed to provide a continuous communications link for shuttle missions, TDRS supports many near-Earth satellites, as well as the International Space Station, the Hubble Space Telescope, and some military applications. Similarly, ESA has launched 2 of what will be a group of 4 data relay platforms to provide a continuous link with near-Earth satellites. Instead of transmitting to ground stations, only visible for brief parts of every orbit, many satellites now send signals up to a data relay spacecraft that can see it for half of each orbit. A network of relay satellites around the globe gives continuous coverage. All major space agencies have been experimenting with data transmissions via lasers, but the EDRS system is the first commercial application of optical communications between spacecraft. Current laser communications techniques between satellites deliver data at 1.8 gigabits per second, 30 times greater than conventional radio links. However, weather-related problems inhibit reliable laser connections between spacecraft and Earth. Transmission back to the ground is via microwave radio in the Ka band. While this is fast, it is still slower than the laser data rates, but the signal can be split into several streams and sent simultaneously. Europe's Copernicus system is a major beneficiary of the near real-time data available via the EDRS system. Copernicus is an Earth observation program relying on a series of Sentinel satellites that send back continuous streams of data about the land, the oceans, and the atmosphere. The Copernicus program is not a limited project. It is designed to collect authoritative data about planetary changes over the long term. To do this, the Sentinel satellites are in low north-south orbits, allowing them to see the Earth's entire surface every 24 hours. This polar orbit is common to every Earth-observing satellite. But not every satellite has access to the EDRS communication system, nor do they generate the vast amounts of high-resolution data that requires it. Most satellites following a polar track rely on the polar receiving installations that they pass above every orbit. On the Norwegian archipelago of Svalbard, the Svalsat installation has 31 radomes to track and download data from satellites in polar orbit. To relay the information to the outside world, twin fiber optic cables each handling 10 gigabits per second, connect Svalbard to the Norwegian mainland. Koenigsberg, the company that operates the facility for the Norwegian government, runs a smaller station in Antarctica. There are close to 1,900 operational satellites in Earth orbit, with a further 3,000 still orbiting as space junk. But there are as many as 20,000 fragments from spent boosters and debris from collisions that must be tracked. Operational satellites are routinely moved when an object approaches on a dangerous course. If this picture appears crowded, it is about to become a lot more complex. The US Federal Communications Commission recently gave rocket company SpaceX approval to launch 12,000 new satellites for its Starlink broadband internet service. Current satellite internet services rely upon a very few large platforms in geosynchronous orbit. Typical users are in remote locations, and while costs are coming down and speeds are improving, latency or response time is sluggish. The Starlink model has thousands of small satellites in low Earth orbit, cross-linked via high-speed lasers. The satellites will be able to adjust their orbital path autonomously to avoid collisions. The company launched its first batch of test satellites in May 2019. The second group, launched in November 2019, consisted of 60 operational satellites. For one company to increase the number of functioning spacecraft by a factor of 6, cost is critical. The satellites are being mass-produced in a flat pack form with a single solar panel. 60 will stack neatly within the fairing of a Falcon 9 launch vehicle. The Starlink satellite design is pushing the latest technology to its limits. Links to the ground are via a phased array, enabling a steerable beam without the need for moving parts. Maneuverability comes from a Hall effect thruster using krypton as its propellant. When released from the booster, the satellites do not require dispensing hardware. They are pushed away by springs in apparently haphazard fashion. At this stage, they can even bump each other and are designed to withstand the impact.
Away from the top of the second stage. This is the highest number of satellites.
Quickly, the satellites orientate themselves and begin spreading along their orbital path. At this point, they can be seen in the pre-dawn or just after sunset. Research astronomers are not happy about the huge number of satellites soon to be in orbit. By 2024, there should be 11,927 Starlink satellites orbiting at 7 different heights. The only satellite constellation remotely similar is the Iridium NEXT system, with 66 satellites cross-linked via the Ka band. They're designed to provide global cell phone coverage, and in 2018, the Iridium company finished the replacement of all its first-generation spacecraft. The upgrade cost Iridium $3 billion. For 200 times more satellites, SpaceX has budgeted $10 billion. Iridium had to pay Thales Alenia to design and build 81 satellites. There are spares both in orbit and on the ground. And it had to pay SpaceX to launch those satellites in batches of 10. With Starlink, the company will take advantage of its own drive to reduce expensive launch services. SpaceX builds its own satellites and its own rockets, so it will only pay cost for hardware and delivery. Recovery of first-stage boosters is now routine, which takes a large chunk out of launch costs. And the protective fairings, always regarded as throwaway items, are now fitted with steerable parachutes for retrieval and reuse, saving a further $5 million per flight. What will give Starlink its edge is its improved latency. In most cases, the system should give even better latency figures than fiber optic connections on the ground, let alone the half-second delay built into systems that send signals 35,000 kilometers up to and back from geosynchronous platforms. For stock markets reliant on high-frequency trading, microseconds make a significant difference. SpaceX believes people around the world will want the service. OneWeb and Amazon's Project Kuiper have announced plans to develop their own low Earth orbiting broadband systems. But with just the smallest fraction of the Starlink constellation in orbit, astronomers are starting to worry. Survey telescopes that use time exposures to map the skies, looking for anomalies like approaching asteroids or exploding stars, have recorded dusk and dawn images marred by Starlink satellites. Researchers from the Large Synoptic Survey Telescope, currently under construction in the Chilean Andes, have run simulations suggesting that as the Starlink constellation takes shape, certain observation times will be unproductive. Yet the Starlink venture itself is still a risk. Satellite businesses like Teledesic and Skybridge, both with big plans, went under. And SpaceX leader Elon Musk admits that success with Starlink is far from a sure thing. Communications with very distant exploratory spacecraft are governed by different parameters. The New Horizons probe, launched in 2006, is equipped with the most advanced digital technology ever to reach deep space. While its primary target was the dwarf planet Pluto, it passed Jupiter in 2007 for a gravitational boost to its speed. At Jupiter, a mere 2.3 billion kilometers from Earth, it transmitted images at 38 kilobits per second. That's slightly slower than an old acoustic telephone modem. At these distances, signal strength from New Horizons was weak, and only the 35 and 70-meter dishes in NASA's Deep Space Network were useful receivers. Even so, the data rate was slowed to deliver a coherent signal. Sending commands to the spacecraft is an exacting process. All instruction code is thoroughly reviewed by different teams before being tested on a simulator. Only then are they sent to the spacecraft. Because the environment around Pluto was so poorly understood, controllers on the ground relied on preliminary images returned by the spacecraft to make a hazard search. Distant encounter observations commenced 7 months before its close pass. As New Horizons approached Pluto in 2015, it had at least 16 different science objectives, along with spacecraft control and data management procedures, all pre-programmed. There could be no last-minute corrections. The spacecraft was traveling at more than 49,000 kilometers per hour, and signals from Earth took close to 4.5 hours to reach the New Horizons probe. During the critical close approach, there was a 22-hour radio silence because the spacecraft could only make its scheduled observations with its high-gain antenna angled away from the Earth. Everything was committed to the 8 gigabytes of storage in the primary data recorder. To retrieve that data took 16 months. At a distance of 4.7 billion kilometers, the New Horizon data rates were down to 2 kilobits per second. Only the 70-meter dishes in NASA's Deep Space Network could detect the signal, and they could not work exclusively with New Horizons. New Horizons kept going into the icy debris field known as the Kuiper Belt. Even as it was still transmitting data from its Pluto encounter, engineers on the ground formulated a series of course adjustments that would take it past object MU-69. the first time a probe was targeted at a body unknown when the craft was launched. In January 2019, New Horizons encountered the Kuiper Belt object Arakoth, formerly known as Ultima Thule. At a distance of 6.6 billion kilometers, data from the spacecraft took 6 hours and 7 minutes to reach Earth, and the data rate had dropped to 500 bits per second. It's still trickling in. Finally, the most distant probe is Voyager 1. It was launched in 1977 and is now outside the solar system at a distance of 22 billion kilometers. The probe transmits data as it is registered, and the Deep Space Network tries to gather at least 16 hours per day of the data stream that comes in at 160 bits per minute. This is roughly equivalent to a telegrapher sending Morse code. Arguably, the most significant scientific instrument in history has been the Hubble Space Telescope. It has changed our understanding of the universe, yet it has posed serious new questions about the nature of matter itself. Hubble has confirmed the widespread distribution of black holes and has viewed light from galaxies more distant than anything previously seen. As well as its scientific discoveries are the stunning images. In 1609, Galileo built an early telescope and soon turned it to the night sky. The telescope was a powerful tool that led to a complete re-evaluation of the Earth's place in the universe. In 1668, Newton invented the reflecting telescope to eliminate the problem of uneven refraction of the different wavelengths of light. The reflecting telescope became the design of choice for astronomers, and in 1781, William Herschel used an instrument he had built himself to discover the planet Uranus. The Newtonian telescope was scaled up to immense proportions, and in 1924, it was with the 2.5-meter Hooker telescope at the Mount Wilson Observatory that Edwin Hubble realized the Milky Way was not the universe, but just one of countless galaxies. But there was still a problem. No matter how mathematically perfect a telescope is, its images are distorted by the Earth's atmosphere, and some wavelengths cannot reach the ground. In 1946, astrophysicist Lyman Spitzer proposed a telescope in orbit above the Earth's atmosphere. The idea clearly outstripped the technology of the time, but by 1966, NASA began launching a series of orbiting astronomical observatories. Only 2 were successful, but the telescopes in low Earth orbit were the first to see the night skies in the ultraviolet part of the spectrum. In the 1970s, plans were drawn up for a large orbiting telescope. Part of its brief was for it to be visited regularly by maintenance crews, something that would become possible when the Space Shuttle went into service. The design called for a 2.4-meter primary mirror ground within very fine tolerances because it was required to function well into the ultraviolet spectrum. Originally known as the Large Space Telescope, it was slated for launch in 1979, but delays in construction led to several postponements, and the Challenger disaster led to more delays. In 1983, the name Hubble Space Telescope was adopted in honor of the man who confirmed that the universe was expanding. Finally, in April 1990, Hubble was ready for launch.
Sound suppression water system has started. T-minus 13 seconds. T-minus 10, go for main engine start. We are go for main engine start, T-minus 6, 5, 4, 3, 2, 1, and liftoff of the Space Shuttle Discovery with the Hubble Space Telescope, our window on the universe.
Hubble has a unique relationship with the Space Shuttle, which would revisit the telescope on 5 different occasions. At this stage, nobody understood just how vital these missions would be. To deploy Hubble, the shuttle Discovery set a new altitude record of more than 600 kilometers. Release of the telescope was routine. It took several weeks methodically checking Hubble's control and communication systems before astronomers working at the Space Telescope Science Institute in Baltimore could see Hubble's first images. Results were disappointing. Images were blurred. The telescope's mirror had been accurately ground, but to the wrong shape. An incorrectly assembled test instrument had been relied upon during manufacture, and nobody had double-checked. Soon a fix was proposed. Because the error was understood, a corrective device could be fitted to the telescope. A series of small mirrors would compensate for the primary mirror's defect. It was called COSTAR, another of those cumbersome NASA acronyms. Training astronauts for the job of accurately installing COSTAR began. The high-speed photometer would be scrapped to make room for it. In addition to correcting the optics, a number of other modifications were set in train. A new wide-field planetary camera would be installed. The original was obsolete. The telescope's solar panels would be replaced. There would be a new electronics processor, extra magnetometers, and 2 gyroscopes would be replaced.
10, 9, and we have a go for main engine start. 5, 4, 3, 2, 1, and we have liftoff. Liftoff of the Space Shuttle Endeavour on an ambitious mission to service the Hubble Space Telescope.
Finally, in December 1993, the mission to repair Hubble began.
Roger, roll, Endeavour.
It took the Endeavour 3 days to catch up with Hubble, and it was clear from the beginning that one solar panel was damaged. The work on the telescope was considerable, and there were 5 spacewalks scheduled. Firstly, the shuttle's robotic arm grabbed the Hubble so it would remain stable while the work was carried out. The work would be shared between 2 teams of 2 astronauts. Over 5 days, the allocated tasks were carried out, with the Space Telescope Operations Control Center monitoring the Hubble's performance as each new component came online. Most of the parts replaced were stowed in the cargo bay for return to Earth, the one exception being the damaged solar panel, which was set adrift in space. All 5 spacewalks went according to plan, with the only major problem being the difficulty involved in closing the telescope's doors. On the 9th day of the mission, Hubble was released. It would take controllers on the ground another month to fully check the telescope's new systems. Hubble had been repaired in December 1993, yet it would take close to 2 months for technicians on the ground to run through a complex series of optical alignments before they could be certain that the telescope was performing correctly. When astronomers finally saw results, they were stunned at the quality it was delivering. The repair mission had been successful. With the services of a powerful new tool finally at their disposal, astronomers at the Space Telescope Science Institute began addressing a pressing list of demands for time on Hubble. In March 1993, a comet had been discovered orbiting Jupiter. Its path suggested that it had only recently been captured by Jupiter's gravitation and that it would soon crash into the planet. No one had ever seen a collision between bodies within the solar system, and opinions differed about how visible the impact would be. Soon, Hubble captured this image of a chain of fragments. Comet Shoemaker-Levy 9 had been shattered by Jupiter's gravitation. The fragments ranged in size from several hundred meters to several kilometers across. Over 6 days in July 1994, Hubble observed the pieces crash into Jupiter's unlit face. As the planet revolved, the impact region showed a series of black swirls. Some of the dark shadows were as large as the Earth, and they persisted in Jupiter's atmosphere for months. Spectral analysis from Hubble revealed diatomic sulfur and carbon disulfide. These had never been seen at Jupiter, yet the amounts detected were too great to have come in with the comet. They had been stirred up from the planet's interior. Scientists learnt so much from observing these impacts, yet the observations almost didn't happen. Just days before the first impact was due, Hubble began acting unpredictably and then went into safe mode. It would not execute any of its instructions. Technicians suspected a memory problem and took measures to switch across to new memory installed on the recent service mission. Things started to improve until the spacecraft reported it had entered zero gyro sum point. It appeared that 2 gyroscopes had failed and the situation had dramatically deteriorated. The problem was traced to a counter that had run out of numbers with which to count. The issue was understood and quickly resolved. The incident underlined just how complex the operations of the Hubble would be, and that the ground engineers still had to learn how to operate the new hardware. Though Hubble functions as a telescope, it is also a spacecraft that must be controlled with exquisite accuracy. Unlike other spacecraft, it has no thrusters. Chemical residue from rocket engines would quickly contaminate the precision optics. To enable it to move, Hubble has 4 reaction control wheels. As they spin, the telescope will rotate in the opposite direction. Each one has a mass of 45 kilograms, and they are controlled by the telescope's computer. Combinations of spin in any 3 wheels will allow the telescope to point accurately in any direction. They are mounted in angled pairs around Hubble's center of gravity. In 1997, on the Space Telescope's second servicing mission, one of the reaction control wheels was replaced. It had developed an electrical fault. So that Hubble can remain pointed accurately, 3 fine guidance sensors positioned toward the back of the telescope will lock onto any of a series of bright guide stars. Hubble only needs 2 guidance sensors to point with accuracy. They are so sensitive, they can detect wobble in the motion of closer stars. The third vital aspect of the telescope's pointing system is its ability to detect the rate and direction of its movement. Hubble is equipped with 6 gyroscopes that register its orientation. These are essential when pointing the telescope in a new direction. The gyros spin at 19,200 RPM and they do wear out. This is why there are 6 units, even though when designed, Hubble only needed 3 to function properly. With new algorithms, Hubble can now point with only 2 gyros, though less accurately. Work has been done to enable it to work at reduced capacity with only 1 gyroscope. Hubble can point with an accuracy better than 2 millionths of 1 degree. This ability to stay fixed on one narrow region of the sky for a very long time led astronomers to perform a unique observation. For 10 days in 1995, they pointed Hubble at a small, empty region of the sky near the constellation Ursa Major. To some, this was folly, a waste of valuable observation time. The results astounded everyone. This empty part of the sky was packed with irregular-shaped galaxies. Some were as old as 13 billion years. Hubble had looked back in time at the formation of new galaxies in a range of shapes not seen closer to our own Milky Way. It became known as the Deep Field Survey. It was the first of a series of similar explorations of areas of the sky in which nothing had previously been seen. Animators have added depth to these images by using spectral information known as redshift, which indicates a body's distance from Earth. This was a completely new area of astronomy, and it was one reason why Hubble had been built, but the Space Telescope was already running into design constraints. Engineers began work on equipment that would upgrade the telescope's performance in the near-infrared part of the spectrum. This would be fitted during the next servicing mission, along with updated support equipment such as a solid-state recorder, which would replace the original reel-to-reel recorder. Yet even at this early stage of Hubble's life, astronomers were realizing its limitations. The distant galaxies it had seen were approaching the extent of its view in the infrared end of the spectrum. Even with enhancements, the telescope could not be kept cold enough to observe the large redshift wavelengths revealing very old, very distant objects. Plans were drawn up for a new, larger telescope, known as the Next Generation Space Telescope, that could explore the most distant parts of the universe. But there was still plenty that Hubble could do better than any other telescope, and there appeared no reason that it wouldn't continue being refitted with the latest technology as it became available. Early in 1997, the Space Shuttle Discovery visited Hubble for a second servicing mission. Astronauts fitted new instruments to improve its reach into the infrared. In 1999, Discovery again visited Hubble. This mission had been brought forward as 4 of the gyroscopes had failed and the telescope had gone into safe mode.
4, 3, 2, 1, and liftoff of Space Shuttle Columbia to broaden our view of the universe through the Hubble Space Telescope.
In 2002, Columbia lifted off with a new instrument, the Advanced Camera for Surveys. It would replace the Faint Object Camera, the last of Hubble's original instruments. When it departed, Hubble was again in peak condition. Less than a year later, at the close of its next mission, Columbia burnt up during re-entry. Foam insulation had come loose during launch, damaging thermal protection tiles. After an exhaustive search for debris and a thorough inquiry, it was decided that the shuttle system was aging. It would be retired upon completion of the International Space Station. All other missions were ruled out. For the Hubble Space Telescope, this was a death sentence. In the corridors of power, Hubble had friends. The sheer beauty of images from the telescope gave it a public profile, and key senators began campaigning for one last servicing mission. After a new administrator took charge at NASA, a final shuttle flight to Hubble was reinstated. Work began on what would amount to a rebuild of Hubble's operational systems, as well as another update of scientific instruments. New fine guidance sensors would be fitted. All gyroscopes would be replaced, and a new set of batteries would replace the originals that Hubble was still using. Within the imaging spectrograph, a power supply had failed, and training began to open up the unit and replace an electronics board. The advanced camera for surveys had also malfunctioned, and its repair work was seen as even more detailed. Because the shuttle now had to operate with a backup, and because Atlantis could not reach the International Space Station from Hubble's orbit, the shuttle Endeavour was prepared for a rescue mission. On the 11th of May 2009, Atlantis sat on NASA's Pad 39A ready for Hubble's final servicing mission. This was to be the most complex servicing mission. It had to deliver the longest possible life for the orbiting telescope. The 14-day operation went according to plan. When problems arose, they were solved, and Hubble was eventually released as the best telescope it had ever been. On the ground, astronomers from the Space Telescope Science Institute waited for the first pictures from Hubble's new, more sensitive instruments. This means the telescope can operate more efficiently, needing less observing time than earlier incarnations. The team was quick to release examples of the new generation images. In the Eagle Nebula, the pillars of creation, thousands of light years from Earth, immense clouds of hydrogen and dust are giving birth to new stars. The 5 galaxies of Stephan's quintet in the Pegasus constellation. 4 of these are colliding. 16,000 light years from Earth, Omega Centauri in the constellation Centaurus is a globular cluster. Stars here are so densely packed that on average there is just 1/10 of a light year between them. While Hubble has been adding to its list of discoveries, everyone understands that without further servicing, the telescope will eventually die. That slow death has already started, and it's the gyroscopes that are failing. Engineers have been careful, operating just 3 gyros, keeping the other 3 as spares. By mid-2018, 3 of the units had ceased functioning. As the last of the 3 gyroscopes held in reserve was brought online, it misbehaved, and all science operations of the telescope were suspended. By recycling power to the unit, a measure akin to switching it off and back on, normal function resumed. As further gyros fail, the telescope will use its star trackers to help it point accurately. Hubble is expected to function well into the 2020s, by which time a new space telescope should be in orbit. The next generation space telescope is now called the James Webb Space Telescope, named after NASA's Apollo-era administrator. The telescope has been completed and is undergoing exhaustive checks before it is launched. It has a giant mirror of 18 hexagonal segments that is folded before deployment. Compared with Hubble, it is huge, yet the complete spacecraft weighs considerably less than Hubble. NASA built the Webb telescope in collaboration with the European and Canadian space agencies, and it will launch on an Ariane 5 from the European spaceport in Kourou, French Guiana. It will orbit at the second Sun-Earth Lagrangian point, a place 1.5 million kilometers from the night side of the Earth, where the telescope can maintain a stable position. A large, very thin sun shield will protect the James Webb, allowing the optical components of the telescope to cool to around 50 degrees Kelvin. Its operational temperature must be very low to allow it to see deep into the infrared end of the spectrum. the mid-infrared instrument needs to be colder still. A cooler using helium as its refrigerant will enable the sensor to function at just 7 degrees Kelvin. The Webb Space Telescope is designed to build on the work of Hubble by seeing further back to the earliest emergence of galaxies, stars, and exoplanets. Our Sun is a star like billions of others throughout the universe. It's a giant nuclear furnace at the center of our planetary system. And although life on Earth is completely reliant upon the Sun, we also need our planet's magnetic field and atmosphere to protect us from extremes of solar radiation. Regularly, the Sun ejects huge blasts of solar plasma, and on Earth, a direct hit by a coronal mass ejection will play havoc with power grids, communications, and satellites. (1859) was a year of extreme solar activity. During September of that year, astronomer Richard Carrington was sketching sunspots when he observed an intensely bright event. Less than 18 hours later, auroras were seen around the world. They extended to low latitudes where the phenomenon is rarely seen. Telegraph operators across Europe and North America reported malfunctions, including electric shocks and sparking wires. This was the first time that solar storms had been linked with auroras and electrical and magnetic disturbances here on Earth, and it became known as the Carrington effect. Since the 1700s, a periodic fluctuation had been observed in the number of sunspots, but a deeper insight into the Sun's behavior would not emerge until 1958. James Van Allen was the chief scientist for America's first satellite, Explorer 1. It was equipped with a cosmic ray detector.
8, 7, 6, 5, 4, 3, 2, 1. Fire command.
The launch was successful, but the orbit achieved was highly elliptical with an apogee far greater than expected. As its altitude changed, variation in the detector's readings suggested that charged particles were trapped in bands around the Earth. These became known as the Van Allen belts. It was a discovery with far-reaching implications. The energetic charged particles that make up the Van Allen belts emanate from the Sun and are trapped by the Earth's magnetic field. They fluctuate with solar activity, and they present a risk to spacecraft that have to pass through them. The previous year, physicist Eugene Parker, working at the University of Chicago, had predicted that a constant stream of charged particles would flow from the Sun. He called it the solar wind. The astronomical community was reluctant to accept this idea. Soon, his theory was vindicated, as early Russian and American spacecraft began detecting a constant stream of charged particles. Solar wind explained why a comet's tail always points away from the Sun. Parker's supersonic solar wind theory predicted a variable stream of plasma, charged particles, permeating the solar system. The Earth's magnetic field deflects most of the solar wind, preserving the Earth's atmosphere. In 1995, the Solar and Heliospheric Observatory was launched. SOHO monitors the Sun from a point where the gravity from Earth and from the Sun exert equal force, keeping the probe in a stable orbit. SOHO gives us a clear picture of the solar wind. Its LASCO instrument obscures the central disk of the Sun, revealing the corona, the Sun's atmosphere. The planets are also clearly visible. The horizontal lines flanking them are due to their brightness overwhelming the camera's sensor. SOHO's Extreme Ultraviolet Imaging Telescope was able to see waves traveling out from solar flares, causing snow-like interference in the image sensor. Solar radiation in the extreme ultraviolet varies from minute to minute and over the Sun's 11-year solar cycle. Solar activity generates tides in the Earth's atmosphere, which increase with altitude. This in turn adds to the drag felt by low-orbiting satellites. Communication systems can also be affected, in particular GPS services. Constantly monitoring the Sun's behavior is important, and in 2010 NASA launched the Solar Dynamics Observatory. It orbits the Earth geosynchronously at an inclination of 28 degrees, which gives it a constant view of the Sun. The SDO observes in a number of different wavelengths that correspond to different temperatures, each one revealing varying activities, from the surface to the corona and to the flaring regions. The Sun is not solid. Rather than rotating, it swirls. At the equator, it spins once every 25 days. At the poles, it takes 38 days. It's in a plasma state, extremely hot matter made up of loose electrons and ions. Plasmas are excellent conductors of electricity, and the movement of the Sun generates a tangle of magnetic field lines. The surface of the Sun, known as the photosphere, has a temperature of around 6,000 degrees Kelvin and is best viewed in the visible part of the spectrum. Here, sunspots appear as dark regions where magnetic flux impedes convection. These are about the size of the Earth. Beyond the visible spectrum, magnetic loops at the same areas become visible. The lower levels of the Sun's atmosphere, the chromosphere, see gravity yielding to the dynamic thermal and magnetic forces, with temperatures increasing to 8,000 degrees Kelvin. Ascending further through the solar atmosphere, a narrow band called the transition region sees temperatures rise to more than 500,000 degrees Kelvin. In the corona, seen here during an eclipse, it rises to 1,000,000 degrees Kelvin. Why this happens is not understood. The atmosphere is where the solar weather is generated. Solar flares appear as bright flashes, bursts of electromagnetic radiation from radio waves to gamma rays. Solar flares from some other stars are much larger than those from our Sun, and sometimes smaller stars, known as red dwarfs, display extreme solar flares. The SWIFT Gamma Ray Observatory is designed for rapidly locating brief bursts of gamma rays and X-rays. In April 2014, SWIFT saw a solar flare emanating from DGCVN. Its initial blast was 10,000 times stronger than any flare from the Sun. It was the first of 7 flares that continued for 2 weeks. DGCVN is a red dwarf, about 1/3 the size of the Sun, and it rotates twice as fast as the Sun. This enables it to generate a much stronger magnetic field. It's thought that the strength of the star's magnetic field is related to the intensity of the flares it emits. Coronal mass ejections are different. They are vast clouds of plasma blasted from the Sun's outer layers. They travel with the solar wind. While they are often linked with solar flares, researchers have not been able to establish a direct relationship. Observing the Sun in different wavelengths yields very accurate temperature readings, and the dramatic rise in temperatures moving away from the surface had scientists completely baffled.
Five, four, three,
In 1990, a new spacecraft was launched.
Ignition and liftoff of Discovery and the Ulysses spacecraft bound for the polar regions of the Sun.
The Ulysses probe was bound for the Sun, but had to go the long way. Solar researchers wanted to have a different view of our star. The solar system coalesced from a vast cloud of gas and dust. As it collapsed, it began to spin, forming a disk. All the planets orbit along the plane of this disk, called the ecliptic. Ulysses would look at the poles, the parts of the Sun that could not be seen from our terrestrial viewpoint. Ulysses traveled via Jupiter, using the giant planet's strong gravitation to change its course. It approached on a path that took it over the planet's north pole. This bent the probe's trajectory beneath the ecliptic so that it could see the Sun from a polar orbit. From Ulysses, we learned that the Sun's magnetic field reverses every 11 years, and that the solar wind from the more dynamic South Pole was faster than from equatorial regions, yet the South Pole had no clear location. The only thing clear about the Sun was that it keeps changing. Now, heliophysicists wanted to be able to see the face of the Sun that was not seen from Earth.
Liftoff of the Delta II rocket with stereo, giving us a three-dimensional look at the physics of our Sun.
The twin stereo probes were launched in 2006. They were in slightly different orbits, one leading the Earth and moving slightly faster, the other trailing the Earth and moving slower. Each year, the two craft separated by 44 degrees, giving each an increasingly different view of the Sun. Because the Sun rotates, sunspots can develop out of sight. As sunspots are key indicators of solar weather, it's important to know just what is about to spin into view. The stereo probes now observe the Sun in 360 degrees. This makes it much easier to plot the direction of coronal mass ejections. Though these happen with reasonable frequency, most will miss the Earth. If they hit, they create havoc in electrical systems and trigger substorms in the planet's magnetosphere. Information provided by the stereo satellites is being used for the protection of power grids and satellites through regular space weather bulletins. Since the 1960s, observers had been aware that auroras would sometimes brighten suddenly, with movement within the auroral curtains increasing. These were short-term phenomena, quite distinct from solar storms that result in auroral activity lasting days. As communication satellites in geosynchronous orbits became more sophisticated, they registered sudden localized falls in the Earth's magnetic field that seemed to coincide with what were now being called substorms.
3, 2, 1. We have ignition and liftoff of a Delta II rocket carrying Themis, NASA's revolutionary journey to study the northern lights.
The Themis constellation of satellites was designed to monitor the behavior of the Earth's magnetosphere. The aim was to measure fluctuations within the Earth's magnetic field and relate any variations to changes detected in the auroras from ground stations in the North American Arctic. Each satellite was equipped with an array of booms to measure the strength and direction of electrical and magnetic fields. After several months, they maneuvered into elliptical orbits of varying eccentricity, with each reaching a high point above the night side of the Earth. The Earth's magnetic field deflects most of the plasma from the Sun. At times of high solar activity, some of the charged particles will spiral into the poles on Earth's day side. On the night side, the field lines are stretched to breaking point, called magnetic reconnection, when the plasma suddenly rebounds along the field lines into the polar regions. In February 2008, 2 of the probes detected a reconnection event, and 96 seconds later, the ground stations registered a sudden brightening of the aurora. The giant loops bursting from the sun's surface are known as flux ropes. They are one of the most basic configurations in plasma. The glowing plasma follows helical magnetic field lines twisting around a central core. The Themis satellites discovered that flux ropes can extend all the way from the Sun to the Earth's upper atmosphere, carrying currents as high as 650,000 amps. Heliophysicists remained baffled by the behavior of the Sun's atmosphere, so a new probe was constructed. Known as IRIS, it was small and simple. It consisted of a telescope, an imaging spectrograph, and ancillary support equipment. It was cheap to build and cheap to launch. IRIS was placed in a polar orbit of the Earth that gave it an uninterrupted view of the Sun. It was able to look at the edge of the chromosphere where the plasma began its steep increase in temperature. Its images were far more detailed than had been delivered by any other probe, and it could discern rapid changes. The waving jets of plasma, called spicules, were revealed in great clarity. There are roughly 10 million spicules across the Sun's surface at any given moment. They can grow to 10,000 kilometers, yet they collapse in 5 or 10 minutes. Researchers have made computer models of the spicules that behave in the same way as the images from IRIS. It is thought that they form through the interaction of charged and neutral particles with the tangled magnetic fields. It seems magnetism must play an important role in the heating of the solar corona and in the high-speed ejection of plasma, but the mechanism is still not understood. There are at least 20 different satellites currently monitoring the Sun's behavior. Most are in orbit around the Earth. While it is important to get beyond the Earth's atmosphere to analyze the solar wind, it has not been possible to get really close to the Sun. Heliophysicists know the particles of the solar wind change not long after they leave the corona. If these particles could be sampled close to the Sun, it would reveal what part of the solar atmosphere was responsible for their extreme heat and their ultra-high speed. Until recently, it was not possible to build a craft capable of withstanding the temperatures in regions that scientists wish to explore. The team behind the Messenger probe to Mercury solved some of these problems with a woven ceramic sunshield which had to face the Sun at all times. Around 2010, work began on Solar Probe Plus, designed to pass the Sun just 6 million kilometers above its surface. A number of different systems have to work in concert to enable the probe to gather data inside the Sun's atmosphere. A carbon composite solar shield surfaced with highly reflective alumina will shade the rest of the craft from temperature extremes. As the Sun is a wideband radio source, the probe is out of contact during its close approaches and must function autonomously. In 2017, the probe was renamed the Parker Solar Probe after Eugene Parker, the physicist who had first identified the solar wind. It was the first spacecraft to be named after a living person.
On a mission like this into new territory, you're going to be in for some surprises. Maybe not big ones, maybe only little ones, but you're going to find that your point of view will have to change to conform with the data. Why is the solar corona, the outer atmosphere of the Sun, at 1 million or 2 degrees when the Sun itself is only 5,600? It isn't because of sunshine, that's for sure. Again, we don't know until we make the flight have a year or two to think about the data.
The Parker probe's launch weight is less than 700 kilograms, which is quite modest. Yet its launch vehicle, the Delta IV Heavy, is one of the most powerful boosters available.
Minus 15.
In the pre-dawn hours of August the 12th, 2018, the final countdown was proceeding.
8, 7,
Eugene Parker was at Cape Canaveral to watch the launch.
3, 2, 1.
There we go.
The probe was headed for 26 highly elliptical solar orbits over 7 years. During its mission, it will make 7 close passes of Venus, slowing each time to sweep closer and closer to the Sun. After separation from its upper stage, the probe first deployed its solar panels. These fold back near the Sun, with a cooling system enabling them to survive. The magnetometer boom unfolded at the rear of the craft, and then the field antennae, to measure electric and magnetic fields and waves, snapped into place. Though the Parker probe leaves Earth at high speed, it uses Venus's gravity to slow down, allowing it to approach the Sun at the appropriate angle. However, as it falls toward the Sun, it will accelerate to 720,000 kilometers per hour. On its outward loops, it will lose speed, but as the mission progresses, the Parker probe will make closer passes at higher speeds. It made its first close approach of Venus after just 52 days. 1 month later, Parker approached the Sun. For 11 days, it was out of contact with mission control, quietly recording data while carefully keeping its sun shield pointed directly at the Sun. Though the heat in this region is extreme, the particle density is not. The sun shield will reach around 1,500 degrees Kelvin, and the protected electronics of the spacecraft will be at room temperature. As the probe loops away from the Sun, it's able to re-establish radio contact and play back the stored data. This is the first image from inside the Sun's corona, taken during Parker's first pass. It shows a coronal streamer. The bright spot is the planet Mercury. The dark spots are image correction artifacts. The Parker probe's second and third passes were at much the same distance and speed as the first, but subsequent passes will be both lower and faster as it continues to use Venus to modify its orbit. In 2024, the Parker Solar Probe will visit Venus for the last time, and its final 5 passes of the Sun will come down to 6.2 million kilometers from the surface. By this time, we should have a clearer understanding of the processes that heat the solar wind and expel it at such high speeds. But whatever we learn about our Sun, it will raise new questions. A clearer understanding of the Sun has led to design changes in satellites and revised management practices of power grids and communication systems. But with new proposals to send humans back to the Moon or on planetary expeditions, we will need to understand more about the potentially hostile solar weather that flows from the star we call our Sun.